because it's the height. It's going to be somewhere between f1 and f0. Okay, and then plus delta x times f of 2.5 plus delta x times f of 3.5 plus delta x times f of 4.5. And then you have the approximation using the middle point of each interval instead of left or right. And of course, it's also an approximation, even though it's maybe a better approximation, but it may not give you the exact answer. So how do you find the exact answer? Take the limit instead of 4, take mn and go to infinity. Same idea, you have the answer. And I-climate reality, you don't even need to have delta x with the same width. You can chop it up any way you like with different width, just simply add all of those areas together, and the answer is take the limit. You have the integral. And this one called the definite integral. Definite integral. Okay, see, chapter 5, we're talking about integral. So I showed you the indefinite integral, which is the antiderivative function. Now, definite integral. The integral with lower bound and upper bound give you the area. It's called definite integral. Okay. Now, the first case is what the function is completely above. What if the function is below? X-axis right here, y-axis right here. You have the curve f of x right here from A to B. You know what? This is going to give you a negative area. Negative area. Why is that a negative area? Because f of x now is all negative number. You time the width, which is the same. Before we chop it off into say, many columns, right? But f of x is now a negative number times delta x positive number, so kind of negative area. That's the same idea. So integral could be a negative area. So by saying area right here, I don't mean it's going to be a physical area, but I don't mean it's a positive number. It could be a negative number that way. Okay? What about this? I have a function like this. This is f of x. Okay? This is A. And this is B. I'll try to show you what this function got. One portion is below the x-axis, another portion is above the x-axis. Say it's intersect x-axis C right here. And you integrate from A to B f of x dx. You're going to have, first part going to be a negative area. Second part going to be a positive area. So this integral, that's definite integral right here, will be the difference of the positive area subtracting negative area right there. Okay. Okay. Now with that idea of idea of definite integral, we have some properties out of it. Let me redraw the first picture. F of x is above. It doesn't matter where it is, okay? So here, A here, B here. So the integral from A to B of f of x dx, again by our definition for now, this is the area of the region bounded by the function f of x, the x-axis, and the two vertical lines x equal to A and x equal to B. And say you have some point C in between. Then integral from A to B is equal to integral from A to C, f of x dx, plus integral from C to B, f of x and dx. What does it mean by integral from A to C? This area right here, A to C. And then integral from C to B. This is the area right here. Okay. Let me check if I missed anything. And we have some properties out of the integral. And I think it works for both definite and indefinite integral. Integral of f of x plus g of x. So sum of two functions dx from A to B. You can put add or subtract, okay? Integral from a to b, f of x dx plus or minus integral from a to b, g of x dx. What is it all about? You have integral of the sum of two functions. You can break it out as the sum of two integrals, okay? And if you have a constant, say integral of k times f of x dx, where k is a constant from a to b, it's going to be equal to k times integral of f of x dx from a to b. Okay? So if you have Saalbach inequality, g of x is greater than or equal to f of x. So graphically, if g of x is greater than f of x means what? G of x is above, so g of x is somewhere up here. Okay? G of x is greater than f of x. Then the area bounded by the function g is going to be bigger than the area bounded by the function f. If you have this, then what? Integral from a to b of g of x dx is going to be bigger, greater than or equal to integral from a to b f of x dx. Okay? And this is 5.1 and 5.2. Let me move on to 5.3. We are talking about the fundamental theorem of calculus. Okay? So, instead of using the definition of area, you have to chop it up, you take the limit, you calculate the limit to find the area. Okay, you see? We approximate, remember, L4 or R4, or L5, R5, R6, R6, Ln, or in general, we take the limit. That's going to take a lot of work. The fundamental theorem of calculus is going to give you a better way, a faster way to calculate that area or the definite integral. This is on 5.3. Fundamental theorem of calculus. Okay, let me redraw. You have a function f of x from a to b, and you want to calculate the area right here. Right. This was integral from a to b f of x dx. What we learned was what? We're going to chop it up into many, many columns. We approximate the area of each column and we chop it up to infinitely many. In other words, we take the limit of the approximation, then we have the exact answer. That's going to require a lot of work. So the fundamental theorem says this. You can calculate this integral is equal to big F of b minus big F of a. Remember what we mean by big F? The antiderivative of the small f right here. And you plug in the value of b, which is the upper bound, and do the same thing for the lower bound. You take the difference. Then you have the area right away. And box that from fundamental theorem of calculus. Okay. So, example then. Example. So, integral from, say, how about 1 to 3 x squared dx. I'm going to use the fundamental theorem right here. Antiderivative of x squared is what? 1/3 x cubed. Was that right? Because what? This is big F of x. It's 1/3 x cubed. And don't forget to plus c, okay? Plus c. That's big F of x. Okay, I'm just writing here because later I'm going to do subtraction, so the c is going to cancel out. 1/3 of x cubed. Check it out. 1/3 of x cubed, take derivative. X cubed derivative is 3x squared. 3 going to cancel out 1/3, so it's x squared. Okay, and we're going to evaluate this function from 1 to 3. This is how people usually write it. And that means what? You plug in 3 first, which is big F of x equal to 1/3 of x cubed, right? So what? 1/3, my 3. 1/3 x cubed now is 3 cubed minus 1/3 of 1 cubed. Okay? So I plug in 3 in here, f of 3 minus f of 1. So this is 9 minus 1/3 is 26 over 3. And this is the area. Let me draw you the graph. You know what function is x squared? It's parabola. Okay? 1 is right here. 3 is right here. This is the area that we are talking about. Area bounded by function f of x equals x squared, which is parabola, and x run from 1 to 3. This is the area that we're talking about. It's going to be equal to 26 over 3. Okay? And now let's extend the concept a little bit more. I want to tell you this. The value x inside the integral notation, let's call it a dummy variable. It means that you can change anything. You can have what? Integral from a to b of f of t dt. It's the same thing. It's going to be what? Big F of b minus big F of a, where little f of t is equal to t squared, for example, or whatever it is. Okay? So you don't really have to use x all the time. What? Integral from 1 to 3 t squared dt. The fx dx dt, ft dt, it's the same thing. You can use any letters inside. Okay, why do I need to talk about that? Because first of all, with our tradition to use x as a variable, but I want to send it out to any other choices that you have. You can use t or s or m or n, whatever. It doesn't matter. Second, because of this. Again, come back to the fundamental theorem of calculus. Let me show you this way. I still have a function. Okay? This function is f of x. Now, a is right here. B is right here. I want to calculate the area from A to B. But let's change the way I think a little. Instead of call this B, let's call this x. And so x could be a variable of changing. Okay, if b equal to 4, b equal to 5, b equal to 6, I have a different area. So I'm talking about what? Integral from a to x. Okay, right. X should be any value. It's not a constant anymore. Okay, and then now I run into a problem because I use x at the upper bound. I cannot use x again for the dummy variable inside of the integral, so I'm going to change to f of t et. Okay, and same idea in here. This is going to be what? Big F of t, but t run from what? T run from a all the way to x. Okay, why is that so good about this? Because you can change the upper bound, you can calculate any area that you like. As long as you change the new value for b, you don't have to recalculate the whole integral thing. And this is a new function. It's called the g of x. It's a function. Okay, and this is what? Big F of x minus big F of a. All I'm doing is what? Replace the b by the x. And to avoid the confusion, I change the letter inside for the dummy variable for the function from x to t. I have this. And this is another part of the fundamental theorem of calculus. Okay? If you have any different value for b, you plug in here, you have a new integral. Say b equal to 5, look at this f5 minus fa, whatever a is. B equal to 6, you got f6 minus fa, you have a new integral. And I think this is enough. The book show you both, and I show you both. Okay. So far in here, I cover all the sections from 5.1 all the way to 5.4. We talk about indefinite integral, which is antiderivative. We talk about the definite integral, which is integral with upper bound and lower bound. And the way we tackle it, by the way, is the name of it. It's called the Riemann sum. Okay, the area below the curve above the x-axis bounded by two vertical lines. And how do we calculate the area of that region? The idea was jumping up this region into many columns. We calculate the area of each column at a time. We add them all up. Okay, and what we have is the approximation, and we try to bring the approximation to the exact answer by taking the limit. N go to infinity, the number of columns go to infinity. We jump it up into infinite many. Okay, and we denote it by integral from a to b. And the fundamental theorem of calculus, I think it's in the 5.3, saying what? This area will be calculated by what? Antiderivative at the upper bound subtract antiderivative the lower bound. You have the answer. So after knowing the fundamental theorem of calculus, you don't have to use the limit anymore. Okay. And let me stop the video clip right here. The next one, I will talk about one very important technique to do the integral called the substitution technique. Let's stop this video clip right here. Thank you very much for watching, guys. Have a good day.